Okay, so I'm going to talk really quickly how to do a first derivative test to use for your titrations. I'm going to talk a little bit first about what I'm doing, and then I'm going to show you how to do it in Excel. The idea behind this, your reminder, is a derivative is basically a slope. And so what we're doing is we're using the points we've measured, and we're taking each. So we're doing basically just slope, right? Rise over run. So what we'll do is we'll take each data point, and so I'm going to give them labels, right? Like in Excel, it'll be labeled like, let's say, we've got a point at A2, A3. These will have numbers in them, and then we'll have B2 and B3. Right, so this represents different columns and rows, and the idea is this data just keeps going down. And then I'm going to make another column where I'm going to look at the difference between these, and so I know what the slope is at each point. So what I'll do is I'll go down to my second data point, and then I'm going to set up an equation. And the idea behind the equation is I want to take the y points, divide them by the x points. So here, I would set up an equation like b3 minus b2 divided by a3 minus a2. And the way I have this equation designed, if I were to take that equation and copy it to lower cells that were below it, it'll automatically increment the index. So it'll go from B3 to B4 and B2 to B3. So I only have to write the equation once, it'll do this for all of them. The goal of the derivative is to identify where your equivalence point is. The closest point to your endpoint will be the highest value for your first derivative, because that's where the change is going to be happening the fastest. Now, one reason we're doing this is because your points are unevenly distributed. So you make volume measurements, and some times you add half a milliliter. Other times you add a tenth of a milliliter or 2/10 of a milliliter. By looking at the first derivative, we can account for that, because I can't always just look at the difference and tell. Sometimes when I look at the difference, there might be 2 points that like, wow, those look really close together. It could be either of them, and this accounts for that. This will also help even more so when you're looking at a diprotic or a triprotic acid, because in those cases, you've got your last equivalence point is usually really clear. But the other equivalence points aren't always. Sometimes when you switch from one equilibrium to the next, there's enough difference in the pKa that you can identify where it happens, but it might not be as clear, especially in real data, not in the data you had in your textbook. And sometimes because of the particular acid, it might just be a really slow slope or a really small change when it's that abrupt. So this calculation will help give you evidence of that. Many times I see first derivative curves where the point for the first equivalence point in a diprotic acid, the first derivative will have value over 100 times lower than the one for the second derivative. Because when or the second equivalence point, not second derivative. Because when you get to the last equivalence point, you're moving to where you're in excess strong base, and a lot of times, at least with the particular acids we're working with, that's such a dramatic change in pH that it makes for a huge shift. Whereas the pKa1 and pKa2, when you're looking at acid, might only be 3 units apart, and so the amount your pH changes is smaller, which makes it more difficult to identify. Now, let's take a look at this with some data. So I've gone ahead and I've put in some points. This is not an actual titration. I made some that looks something like this, and I can make a graph of this, and I'll insert that. I'll make a graph. And this one we tend to use connected points because that's implied that each of these goes to the next. And if you were turning this graph in, you would need to create some labels, right? You need to say the x-axis is volume, the y-axis is pH, label it as in milliliters. I'm not going to write that for right now, though. But I can tell the equivalent point is somewhere around like this 11 or close to 12 range, right? So what I want to confirm, though, is I'm not sure which of the particular data points. Is it 11.9 or 12? Which one of these points is it likely? Or maybe it's this one down here at 11.7, or maybe this one up here at 12.3. So I'm going to go over here. Let me zoom in some more. So I'm going to do a first derivative. You don't have to label it exactly like that. Whatever you for you. Keep track of it. Now I'm going to the second point because the first one I can't subtract anything from because there's only one data point. So I make an equal sign. And I'm going to make sure to put this in parentheses. So I'm doing everything in the numerator first, everything in the denominator, and then I'm dividing them. If you don't put parentheses around things, it'll be dividing the wrong things by each other, right? Because it'll think you've got one number minus a fraction minus another number instead. So I have B3, which represents the current data point and the y value, because that's my pH, minus B2. So first I'm measuring the difference between the current pH point and the previous one. So how much did it go up? And then I'm dividing that by how much I added. So my volume change was A3 minus A2. And I press enter, and that calculates for me. The first derivative is 0.516. I'm going to scroll out some. Now, by itself, that one data point isn't all that helpful. But if I go here, and you'll notice how my cursor changes from like an open cross to this like closed one. If I click on this little dot here and I hold down and I scroll down, it copies the equation for me, and then it does it for me. And when it does this, it increments it. So each time it's adding, if you notice, if I click on these, if you look at this little window I'm highlighting now, sorry to make that. Whichever one I do, you'll notice it's changed the values. And so as I scroll down, it changes it by adding one to each. Now I'm going to make a graph of this. So I'm going to do A, hold down Control, click C. This will let me do A and C. I'm going to make a graph of this now. In my first derivative graph, you'll notice there are 2 points that are close, but the highest one is here, is at 12. I can also go into my data here, and I can see that at 12, it's 11.1, at 11.9, it's 10.8. Wherever the value is largest, that is the point that is closest to your equivalence point. It might not be exactly it, because you can't know what's it like when volume is 11.95. But based on my measurements, I would now say my first derivative was, my first equivalence point was at 12 milliliters, 12.0, because my first derivative was highest here. Now, with this particular data set, and with most of your monoprotic acids, it'll be somewhat clear, I think, where it is, but this can help if you've got 2 points you're not sure about. This will be more helpful when you get to your diprotic acid, where when you look at that data set, you'll likely have a first derivative where the second equivalence one will be really obvious, the first one may not be quite as clear. So hopefully that helps out, and that's how you can make a first derivative graph to include with your stuff. Just don't forget to label things when you actually put these things in your paper.